This is the second class on partial differential equation. In the first class, we have introduced partial differential equation and argued that it is a very useful tool for framing the dynamics of a system. And then we classified the second order partial differential equation in two and more variables. Finally, we introduced the separation of variable techniques, in which case the solution is assumed to be the product of functions, one function each for each of the variable, and as a result a partial differential equation in n variable ultimately decomposes to n ordinary differential equations, and which can be solved by using standard technique. To elaborate the separation of variables technique, we shall solve Laplace's equation in Cartesian coordinates in 2 and 3 dimensions. So Laplace's equation in Cartesian coordinates. Now the Laplace equation in Cartesian coordinate, the original equation is, which now becomes del 2x in Cartesian. In 2D, this becomes, in 2D means x and y, this equation is del 2x, del x2, del 2y, del y2, operating on phi. Here phi is a function of xy as equal to 0. As per separation of variable technique, we use phi of xy is equal to capital X of x and capital Y of y. We plug this into this equation. The first derivative is y times x double prime. The second part gives you x times y double prime is equal to 0. Here x double prime means the double derivative of capital X with respect to x, and y double prime means double derivative of capital Y with respect to small y. Since capital X is a function of x only, its derivative means with respect to the relevant variable x, and so for this. So there is no confusion about the notation. Capital Y will never be differentiated with respect to x. Even if one does so, it yields 0. So for non-trivial solution, this equation gives us x double prime by x is equal to y double plus y double prime by y is equal to 0. If we change the side, then we have x double prime by x is equal to minus y double prime by y. Now we choose the separation constant. The separation constant, if we know that the solution has periodicity in the x direction, so we use it minus k square, where k is real. K belongs to real number, so in that case x equation becomes x double prime plus k square x is equal to 0, with the solution x of x is equal to either a cos kx plus b sin kx or a e to the power I kx plus b to the power minus I kx. This represents a wave traveling along the positive x direction, and this is a wave represents traveling along the negative x direction. So we call this to be the progressive wave solution, and this is the stationary wave solution. If we choose the solution so that it has a periodicity in x direction, then the y equation becomes y double prime minus k square y is equal to 0, which has a solution y of y is equal to c e to the power minus ky plus d e to the power plus ky. That is to say, if we want to solve Laplace's equation in Cartesian coordinate system in 2D, then we have sinusoidal solution in one direction and exponential solution in the other direction. So the solution of Laplace's equation, we can have two types of solution. One is that phi of xy, when we assume it to be periodic in x direction, then it is a cos kx plus b sin kx times c e to the power minus ky plus d e to the power plus ky. Or we may interchange the role. The solution may have periodicity in y direction, then it will be a e to the power minus kx plus b e to the power kx, exponential solution in x direction and periodic solution in y direction. So this is y. So these are the two alternative solutions. Depending on the boundary condition of the problem given, we may choose one of the solutions. Let us consider a situation in which case we have an infinitely long sheet with L. This is L with L, and it goes to infinity. This sheet is heat is supplied from this end, so that this end has a fixed temperature theta 0, and all other sides have temperature theta is equal to 0. And the problem is to find out the steady state temperature at a point xy. In this, the heat conduction is being governed by diffusion equation or heat conduction equation. In the non-steady state, the equation is this is the diffusion equation which governs the heat conduction in a non-steady state. In the steady state, this is equal to 0 in steady state. In the steady state. So the equation reduces to Laplace's equation. This is a two-dimensional problem, so we need to solve Laplace's equation in 2 dimensions to get the temperature at a point. Now, if we choose this direction to be the x direction, then it is the y direction. You see that the function has 0 at x is equal to 0 and at x is equal to L. So if we choose the solution in this form, this condition cannot be satisfied. But if we choose the solution in the first alternative, then the first condition gives a is equal to 0 and the second condition gives KL is equal to n pi. So we opt the solution in this form. So the solution for theta of xy is equal to a cos kx plus b sin kx times c e to the power minus ky plus d e to the power ky. Now the first boundary condition is this one. This is theta of 0 y is equal to 0. This is theta of Ly is equal to 0. This is the theta of 0 x is equal to theta 0, which is, and this is the, and the last condition is that theta at any value of x as y tends to infinity has to be 0. Because heat is being supplied, so temperature gradually decreases as we go up the y-axis, and at a very large distance away from it, the temperature of the seat will be that of the surrounding, and theta is the temperature of the seat in excess to the surroundings. So the boundary condition is that theta of x is equal to 0 y at any y is 0. If we put this, we get a is equal to 0. So this part is not there. Now theta at x is equal to L and any value of y is 0. This gives, for non-trivial solution, sine KL is equal to sine of KL is equal to 0 is equal to sine of n pi, which gives the discrete values of Kn is equal to n pi by L. Now this condition that theta at any x y tends to infinity goes to 0. This means that this part has to be 0, otherwise this has an exponential divergence, which indicates that d is equal to 0. And the lastly, so we have the solution, this part is not there, so this solution reduces to, we define a new constant E, D and B and C coupled together to a new constant E, and the solution depends on n also. So this is En, because En has different values. Then we have sine of n pi Lx, and we have e to the power minus n pi Ly. This is the solution for a given n, and n, the restriction on n is that n can have values 1, 2, 3, integral values of n. Now the last condition, that is this constant temperature. If we apply this, so we get theta 0, which is a constant. This part theta 0 is equal to y is equal to 0. If we put y is equal to 0, it is En sine of n pi Lx, and this part is, as y is equal to 0, this part is 1. So this is the En. If we hit this plate uniformly over here, then theta 0 will be a constant. For non-uniform heating, theta 0 will have dependence on x. So in general, theta 0 has x dependence, and we can sorry, so, sorry. Sorry, this part, up to this part it is okay. So we have solution for different values of n. So the general solution theta, the general solution of theta of xt is equal to sum over n is equal to 1 to infinity theta n of x y, and where theta n is given by this result, summation over n is equal to 1 to infinity en sine of n pi lx e to the power minus n pi ly. Now we apply this is the general solution. Now we apply that theta 0 is equal to theta at x0. So theta 0 may be a function of x, theta 0 may be a function of x, summation over n en sine of n pi lx. Now to evaluate en, we multiply both the sides with sine of m pi lx and integrate it over L, integrate over x from 0 to L, and we get the value En. So this is simply as we have done in the case of Fourier series. But here one thing has to be kept in mind. The range of integration is x integration is 0 to L, in which case the part should be 2 pi n by Lx, but here the r, so in which case it is double of this one. So this is an half range series. Half range series. Sorry. So we are to, in evaluating the range, we are to extend it from 0 to L. Integration dx has to be extended from minus L to plus L dx. And for the part 0 to minus L, we can expand it as per our wish. If we expand it as an odd in multiple, then the calculation becomes very simple. A odd extension, then the calculation would become very simple. Now as the second example, we consider two more examples. One is this. The problem is to solve Laplace's equation in 2D Cartesian coordinates with the boundary condition this. Now you see that x, the solution is 0 at x is equal to 0 and x is equal to a. So this type of solution satisfies this equation. Furthermore, since the solution is 0 at y is equal to 0, c plus d is equal to 0, so you need not to keep two constants. This condition gives a is equal to 0, this condition gives k a is equal to n pi, this condition gives c plus d is equal to 0, so this part will be obtained in terms of sine hyperbolic of sine hyperbolic ky, and finally the constant can be evaluated from this relation. Now come to the third example. Here the waveform, the solution is 0 at y is equal to 0 and y is equal to b. So such solution does not satisfy this condition. So we are to go to this one. In which case, if we put y is equal to 0, then this c is equal to 0 and y is equal to b gives k is equal to m pi by b. and this condition allows us to determine the constants a and b. So that's all about Laplace's equation in 2D. Now I come to Laplace's equation in 3D. And now in 3D, the equation is del 2 del x2 del 2 del y2 del 2 del z2 phi of x y z is equal to 0. We use phi of x y z is equal to x of x, y of y, z of z. So if we put this first part gives you x double prime y z, second part gives you x y double prime z, and the third part gives you x y z double prime is equal to 0, where we use as usual x double prime is the double derivative of capital X with respect to small x, y double prime is the double derivative of capital Y with respect to small y, and z double prime is the double derivative of capital Z with respect to small z. Note that here we haven't used any partial notation for partial differentiation because capital X has only small x dependence. For non-trivial solution, we divide all through by x, y, z, and we have x double prime plus x plus y double prime by y plus z double prime by z is equal to 0. If we write it as the left hand side is a function of x only and the right hand side is independent of x, it depends on yz and variable y and z, and they are same for all values of x, y, z. So each side must be equal to some separation constant. If the separation constant, if we choose the solution to have periodicity in x direction, we write it as kx square, where kx is a real quantity, so that the x equation becomes x double prime plus kx square x is equal to 0, which has a solution x of x is equal to a1 cos kxx plus it's better to ax bx sin kxx, or we can write in terms of travelling wave solution x of x is equal to ax e to the power I kxx plus bx e to the power minus I kxx. Now x equation has been separated out. Now we are left with this equation. So the equation is y double prime plus y plus z double prime by z is equal to kx square, which will get y double prime by y is equal to kx square minus z double prime by z. If we choose that the solution is periodic in y direction too, we define it as ky square, where ky is again a real quantity. In that case, y double prime plus ky y is equal to 0, which gives the solution of y in the form of like this with x is replaced by y. So by sine of ky y, or now that we are left with the z equation. We get, if we take it on the other side, then we have z double prime by z is equal to kx square plus ky square. Let us call it kz square, where kz is equal to kz square is equal to kx square plus ky square, and the resulting equation is z double prime minus kzz is equal to 0. This has exponential solution. Az e to the power kzz plus bz e to the power minus kzz. So we see that when we solve Laplace's equation in three-dimensional Cartesian coordinate system, we may choose the type of solution, that is exponential solution or a sinusoidal solution in two direction. As we have chosen the solution to be sinusoidal in x and y direction, then the solution in the z direction comes out to be in the form of exponential. We could have choose this constant to be plus ky square. In that k plus ky square, in that case that solution in the y direction will be exponential of this form, that is of this form, and here the kz square will be kx square minus ky square, and depending on the relative magnitudes of kx and ky, z may be exponential or sinusoidal. If ky square has greater magnitude, then kz would be negative and the solution will be sinusoidal, and if kx is higher in magnitude, then the solution will be exponential. That is, so we conclude that when we solve Laplace's equation in three-dimensional Cartesian coordinate system, at least one solution will be exponential and one will be sinusoidal, and the third one may be sinusoidal as well as exponential. So we can have sinusoidal solution in two direction and exponential solution in one direction, or we may have exponential solution in two direction and sinusoidal solution in the other. So this is regarding the theory of Laplace's solution of Laplace's equation in Cartesian 3D Cartesian coordinates using separation of variable technique. Now we shall apply the theory to the solution of few simple problems. Now, as an example of the solution of Laplace's equation in three-dimensional Cartesian coordinate system, we consider the steady-state temperature distribution in a cuboidal box. Since the steady-state temperature distribution is given by the solution of Laplace's equation, we consider the example in such a form that the cuboidal box is such that it is It is at zero temperature. Sorry. This is origin, this is x-axis, this is y-axis, this is z-axis. So this is the x is equal to 0 plane. At x is equal to 0 and x is equal to a, the temperature is 0. So this phase and this phase has 0 temperature, and so is y. This is the y is equal to 0 plane, this is y is equal to b plane, where also the temperature is 0, and this is the z is equal to 0 plane, which is at a 0 temperature, and this part, this surface is at a constant, at the temperature v of xy. It is so the solution must satisfy the condition that solution is 0 at x is equal to 0 and a, and at y is equal to 0 and b. The exponential solution cannot satisfy these two conditions. So we assume a periodic solution in x direction. So we write x is equal to ax cos kxx plus bx sine kxx. X at 0 is equal to 0 implies ax is equal to 0, and x at a is equal to 0 implies kx a is equal to n pi. So kx is quantized, kx of n is equal to n pi by a. Similarly, we choose y solution to be ay cos ky y plus by sine ky by y. Y is equal to 0 condition gives, gives ay is equal to 0 and y at b is equal to 0 gives kyb is equal to m pi, that is ky of m is equal to m pi by b. So that kz square is equal to kx square plus ky square is equal to pi square n square by a square plus m square by b square, and the z direction, the solution in the z direction is kz of z is equal to az e to the power kzz plus bz e to the power minus kzz. The condition that z at 0 gives az plus bz is equal to 0, so that we can write it as az e to the power kzz minus e to the power kzz. So this is equal to twice az sine hyperbolic kzz. So the solution becomes theta depends on two numbers n, m, x, y, z. The constants are this constant ax, this and this. We combine this solution as E n m. Then we have sine of n pi ax from x solution, sine of m pi by from y solution, and sine hyperbolic kz from z direction. This solution is valid for all n and m from 0 onwards. So the just general solution is summation over n m ranging from 1 to infinity phi of n m x y z. This is the general solution. So this is summation over n m e n m sine of n pi a x sine of m pi by sine hyperbolic kzz. Now we apply the boundary condition, that the last boundary condition, that at z is equal to c, this part happens to be a constant, and we have v of xy is equal to theta at xyc, which is sine this part will be kzc. Now this is a double Fourier series, and we can multiply this one with sine of n prime and this with sine of m prime and get the result, and get the evaluate ENM in terms of Vxy. This is an example of the solution of Laplace's equation in 3D. And the second example, we consider a conductor in the form of a cube, a cubic conductor. We know that the conductor surface is an equipotential surface. The conductor is not grounded, so the potential is constant along all the 6 faces, and this constant value is phi 0. So the solution in the x direction we choose in the form of the traveling wave. Ax e to the power I kxx plus bx e to the power minus I kxx. Similarly, y direction and z direction. The boundary condition is that x is equal to 0 is equal to phi 0 is equal to x at a. If we apply this, we get ax plus bx is equal to ax e to the power I kxa plus bx e to the power minus I kxa. If this relation has to vary, the only solution is that kx is equal to 0. So kx is equal to 0. So the solution is a constant, in the form of a constant. Similarly, so x solution becomes with kx is 0, this is ax plus bx, we call it another a prime of x, a new constant. Similarly, the solution in the y direction is chosen in this form, and we call y of y is again another constant, a y prime. Now coming to the z direction, the solution in the z direction also satisfies this. So z of z is equal to AZ prime. So we conclude that the solution for the phi x y z is x of x, y of y into z of z. This is ax prime, ay prime, az prime, which is the constant potential of the conductor. So we can solve this to show that the potential at a point within the conductor Q conductor is 0. Zero is phi 0. So the potential at any point on the surface of the conductor as well as inside the conductor is constant. So if we and if we find out the electric field, which is 0 within the conductor. That's all about the solution of Laplace's equation in Cartesian coordinates. In the next class, we shall discuss the solution of Laplace's equation in spherical polar coordinate system.